Dr. Rylan Grace wakes up on board a spaceship with no memory of who he is or what he is doing there. He quickly learns that he is in orbit around the star Tau Ceti, 11.9 light years away from Earth. His mission is to learn more about the interstellar pest known as Astrophage, which is slowly blotting out the Earth's sun and causing catastrophic global cooling. This is the premise of Andy Weir's novel Project Hail Mary and its very successful film adaptation starring Ryan Gosling that I have already seen 3 times. While I will likely write out more personal feelings about it later, I will say here that it is exactly the kind of film I needed right now. Intriguing science fiction concepts, beautiful cinematography, and a hell of a lot of heart. However, I would like to delve into the basics of the science of this movie. While a lot of this is science fiction, the alien Rockies technology that revolves around solid xenon is scientifically incoherent, I fear, the basics of it are actually mostly really solid. From the mass energy conversion that governs the life cycle of the astrophage, to the relative timeframes caused by near speed of light travel, things mostly look pretty good. However, by the end of this video, I promise that not only will you have a refresher on these physics fundamentals, but you will see 2 errors present in the book and movie. One that is largely inconsequential, and one that kills not just Rylan Grace, but the whole of Earth as well. But first, the basics. And where else is a good place to start than with the little space dots that could? To investigate, let's go to our lab real quick. Welcome to the laboratory. It's a kitchen. It's just a kitchen. This is an astrophage cell. It is a single-celled organism about 10 microns in diameter, or about half as wide as a thin strand of hair. So, very small little guy. The astrophage are resilient little troopers, able to survive in the cold vacuum of space and on the surface of our sun by maintaining an internal temperature of just under the boiling temperature of water. Their life cycle is relatively simple, so to illustrate, let's take how it plays out when they settle in our solar system. First, they find the sun. Stars are their feeding ground, and they sit on the surface of the sun, absorbing the frankly ridiculous amounts of energy it spits out every day. Then, when they're all full, it's time to do the other thing that all living creatures do besides eat: reproduce. To do this, they need to be in the presence of a carbon dioxide atmosphere. So, to go forth and multiply, they lock onto the nearest planet with a carbon dioxide-rich atmosphere, in our solar system's case, Venus, make a beeline for it, and presto, now you have more astrophage. Then, once they have reproduced, it's time to eat again, so back to the sun they go to repeat the cycle. However, not content to just hang out on one star, astrophage can spread to other stars. The book informs us that they have a maximum travel range of about 8 light years, but in our galactic neck of the woods, that's plenty to be able to spread out across several stars with relative ease. So the big question, how do astrophage cells eat sunlight? How do they get from the sun to Venus or travel the incomprehensibly vast distances of interstellar space? The answer? Einstein. E equals mc squared. This is an equation we've all seen a lot. But what does it actually mean? The answer, according to Einstein, is that this is an equation that describes the energy that exists inside any mass in the universe. If you were to take an object and just turn it into energy, this equation describes the energy output of this interaction. This equation is at the very heart of the astrophage life cycle. As our friendly astrophage cell sits on the surface of the sun, it turns the radiation coming from the sun into neutrinos, ridiculously, stupendously tiny particles that have so little mass, we only discovered that they have mass at all in the 1960s. These neutrinos build up inside the astrophage cell until it's all full. Then, when it's good and ready, it turns this mass back into energy to move around. According to the book, a single astrophage cell can hold up to 17 nanograms of neutrinos, close to the weight of a centimeter cutting of hair. This might sound extremely small, but this comes to about 1.5 million joules worth of energy when released. 1.5 million joules all packed into a little cell about a hair's width across. To get an idea of how insane that is, if you wanted to run your house's electricity off these little things, you would only need 40 individual astrophage cells per day. If you wanted to run an electric car off these buggers, you'd only need 100 cells per charge. This is all very cool when we're dealing with these small numbers, but things get destructive extremely quickly the more you pile up the astrophage. In the film, there's an accident where astrophage is activated, blowing up an entire building. The mass of astrophage it took to do that? 1 milligram, about the weight of a grain of salt. It took 64 kilograms for Little Boy to deliver a 15 kiloton explosion over Hiroshima. To create a similar explosion with astrophage, you would only need enough to make up the weight of this reason. If you were to fill this jug of milk with astrophage, first it would weigh about 80 kilos because enriched astrophage weighs about 40 kilos a liter, but if you were to detonate it, you get an explosion 35 times more destructive than Tsar Bomba, the largest nuclear bomb ever detonated on our planet. Astrophage is some serious shit. Okay, so we know astrophage can turn energy into mass and vice versa, so how does this help it move? The answer is light. When an astrophage is ready to move, it specifically turns its stored mass into infrared light. This is how we discover that we have an astrophage problem in Project Hail Mary in the first place. The emissions of the astrophage moving from the sun to Venus and back again traces a line of infrared light between the star and the planet that comes to be known as the Petrova line. But yeah, light comes out one end of the astrophage cell and it moves in the opposite direction. Now, this may seem strange. Light definitely has no mass, so how can it move anything? Well, the answer is that the famous E=mc² equation is only a part of the picture. There is more to Einstein's energy mass equation, and it looks a little something like this. Now, the equation is not just in terms of mass and the speed of light, but also in terms of the object's momentum. If an object is at rest, its momentum is 0, which is where we get the famous E=mc² equation that tells us how much energy is stored in a stationary mass. However, let's take the example of light, which has no mass at all. If we set our mass to 0, in the end we get an equation that looks like this. Light, despite having no mass, still has momentum. Now, in our universe, momentum is always conserved. For example, if two objects crash and bounce off each other, the total momentum of the two objects will be exactly the same after the crash as before. The same applies to our little astrophage. Let's say our little guy is sitting on the sun completely still, its momentum is 0. Then it shoots some light out with momentum in one direction to go to Venus. Because we started with a momentum of 0, the total momentum of the astrophage and the light must always be 0. So when the light goes in one direction, by nature, the astrophage must shoot off in the other direction. Presto, propulsion by light. Incidentally, this does apply to all light sources, it's just that the momentum of the light coming out of your phone, for example, is so spectacularly tiny compared to the size of the phone, so as to be pretty much non-existent. Also, you can calculate the momentum of a single photon of light using its wavelength. Thanks to the novel, we actually know the exact wavelength of light the astrophage emit when they're in motion, 25.84 microns, which is in the infrared range of light. So we can find the momentum of a single photon emitted if we wanted to. Now, up till now, all the physics regarding the astrophage has been pretty accurate, but there are a couple of inaccuracies worth mentioning. The first regards the storage of energy as mass. Now, theoretically, there is no problem with energy being converted into neutrinos and vice versa. It seems legit, but neutrinos are notoriously elusive. 100 trillion neutrinos pass through your body at any given second, and they rarely, if ever, interact with it at all. The only real hope anyone has of detecting neutrinos is by building gigantic pools deep underground. And even then, you detect a comically small percentage of the neutrinos that pass through the detector. There is a reason we didn't even realize they had mass until the 60s. They're bloody difficult to observe. So the idea that these astrophage can just hold neutrinos inside of them is unlikely. To be fair, the novel does acknowledge this as bizarre, but the scientific attitude held by everyone in the book is something to the effect of, look, we'll work it out when we don't have an interstellar pest problem blocking out the sun, which gives Weir a plausible out to say, look, it works, don't think about it. The next glitch regards the way astrophage reacts to light. As I said earlier, the astrophage cell is only 10 microns across. According to all known laws of physics, an object cannot interact with any light with a longer wavelength than itself. Take a microwave, for example. You see this grill on the screen of the microwave? These holes in the grills are just millimeters across. However, the wavelength of the radiation it uses to heat up food is about 12 centimeters long. This is great for penetrating your TV dinner and heating it up, but it's too long to be able to get through these millimeter wide holes. This is why you can watch your meal spin around happily without the microwave radiation melting your face off. It's physically impossible for the microwave radiation to get you. The next important idea is that of spectral signatures. Every element and compound has a spectral signature of what light it can interact with, either absorbing or emitting it. Why? Particle physics. The upshot is that these form sort of universal barcodes. This is how we can guess what other stars and planets are made of without actually going there. look at the light coming off the object, look up the spectral barcodes, and off we go. So let's put these ideas together. In the infrared spectrum, carbon dioxide spectral signature tells us it should absorb or emit a lot of light around 4.26 microns and 18.31 microns. By our known laws of physics, this should make our astrophage very happy. It can see 4.26 micron light because the wavelength is shorter than its body, so the moment it sees an object absorbing or emitting a bunch of light at that wavelength, it can go and head in that direction. However, in the novel, Weir claims that the astrophage can also see the 18.31 micron wavelength, which should be impossible because that wavelength is nearly twice the diameter of an astrophage cell. The characters in the book acknowledge this as impossible, but it happens anyway. The scientists in the book postulate that this is somehow tied to the same quirky behavior that allows astrophage to hold neutrinos without them escaping, but this strikes me as something Weir didn't have to write in. Like, he could have just said that the astrophage can only see carbon dioxide from the 4.26 micron light, and we still would have all been cheering. The final problem is density. Earlier I said that an enriched astrophage has a density about 40 kilos per liter. I arrived at this number by assuming that an astrophage cell is a perfect sphere, insert that old physicist joke about a spherical cow in a vacuum, finding its volume based on that assumption and its diameter of 10 microns, then dividing the enriched mass by that volume. 40 kilos a liter. Heavy as hell, but given the numbers provided to us, was reasonable. But the trouble comes in the mass of an astrophage carrying no energy mass. In the novel, Ryland Grace measures the mass of an unloaded astrophage at 0.02 nanograms. If you run the same calculations that I did for the enriched astrophage, you get a density of 0.0382 kilos per liter. Wow, that's pretty light. Just one small problem. Astrophage is a water-based life form. The density of water is, by definition, 1 kilo per liter. You can't have a water-based life form that is less dense than water. So let's pretend that Weir is a liar whose pants are on fire. The average mass of a cell in the human body is 124 nanograms. For fun, let's say 2 nanograms. If we plug that mass into the volume I found earlier, we get a density of 3.82 kilos per liter. Quite a bit heavier than water, but in the realms of believability for the density of such a creature. And the great thing is, this doesn't actually throw off the approximate examples I gave earlier about how much astrophage you need to blow things up, so it's a far less consequential error than the previous ones. This covers the basics of the physics that govern the life and times of our humble astrophage. Based on all of this maths, Eva Stratt and her band of scientists come to the conclusion that, while being a pest that will kill us all, astrophage makes the best possible rocket fuel. Load a spaceship up with astrophage, develop an engine that can activate it consistently and safely, and Bob's your uncle, we're going to space and at speeds never attained by humans ever before. By the way, the sheer amount of infrared light shooting out the back of the Hail Mary is, as I'm sure you can imagine, insane. This is why the atmosphere of the planet Adrian catches fire during the fishing sequence. The sheer amount of infrared light coming out of the engines is straight up igniting the atmosphere. This turns out to be vital to save the planet, as an expedition to the star of Tau Ceti, a star that doesn't seem to be having the same pest problem as the rest of the local star neighborhood, could hold the key in saving our solar system from its astrophage invasion. The question is, how do we get there, and how fast can we get there? In the novel, we learn some details about the principles behind Ryland Grace's fateful flight to Tau Ceti. The star is 11.9 light years away, so it was an extremely long journey. Fortunately for Grace, he was in a coma for the entirety of the flight, so he could wake up bright and ready to do the job. Two vital questions pop up with interstellar travel, especially in the context of a time-sensitive mission to save the world that relies on the astronauts getting there safe and well. 1. How do we get there as fast as possible? 2. How do we keep the astronauts as healthy as possible? The answer to both questions, as it turns out, is the same. Constant acceleration. For the first half of the trip, the Hail Mary points towards Tau Ceti. The engines are switched on and the ship takes off. For the first half of the trip, the ship constantly gets faster, adding velocity at a fixed rate. For every second that passes, the ship goes 14.7 meters per second faster. This might seem like a small change on the cosmic scale, but this acceleration adds up fast. At this rate, after an hour, we're already doing 53,000 meters per second. By the end of the day, we're doing 1,000,000 meters per second. Already, the first benefit of this form of space travel is showing itself. If we're constantly adding to our travel velocity, we can get up to good fractions of the speed of light relatively quickly. The theory of this is actually relatively easy. The biggest problem here is fuel. In the real world, there doesn't exist enough fuel to get us to these insane speeds. Fortunately, Ryland Grace has Astrophage, so he's chillin'. However, you have to slow the ship down if you actually want to get to Tau Ceti. If you get up to ludicrous speeds, but then don't have a plan to slow down, you shoot right past your destination, and then Ryland Grace's name may as well be Will Robinson, because he'll be lost in space. So to make sure that this doesn't happen, halfway through the mission, we turn the ship around, so now it's facing away from Tau Ceti. We keep the engines firing with the same acceleration we've used this whole time, but now with the engines facing Tau Ceti. So now instead of adding 14.7 meters per second to our velocity every second, we are subtracting it. The ship still feels 14.7 meters per second of acceleration, but because this acceleration is in the opposite direction of its travel path, the ship slows down. To put it simply, the fastest way to travel to other stars is to constantly speed up for half of the flight, then constantly slow down the other half, so we get there at a manageable speed. Honestly, it's a pretty elegant solution to the problem of interstellar travel. If we do this for the trip to Tau Ceti, we can hit a peak velocity of 99% the speed of light, which is bananas. And it provides an extra benefit too: artificial gravity. You know how when you're in a car and someone absolutely floors it and it feels like you're being pulled back into the seat? Technically speaking, you're not. By Newton's first law, an object at rest will stay at rest unless an external force acts upon it. Simply, an object traveling at a fixed speed will continue to move at that exact speed unless an outside force interferes. In this car example, you are an object at rest. According to Newton, your body wants to stay at rest. When your mate stomps the gas pedal and goes from 0 to 60 in 3.5, your body is still trying to stay at rest, but the car isn't letting you. So it's less that you're being pulled back into the seat, and more that as the car accelerates, it's aggressively pushing into you and forcing you along for the ride. This is the concept behind the idea of G-forces due to acceleration and how we get some nice artificial gravity on board the Hail Mary. As the Hail Mary accelerates towards Tau Ceti, everything inside it feels a force of being pushed along for the ride. At the acceleration factor of 14.7 meters per second I mentioned earlier, this will feel like standing on a planet with 1.5 times the gravity of Earth. If we were to express this in terms of Earth's gravity, we would say an acceleration of 1.5 g. To put it another way, I weigh about 80 kilos on Earth. If I was on board the Hail Mary, I would feel like I would weigh 120 because of the g-force caused by the constant acceleration. Then, when we turn the ship around for the slowdown period, we still feel that same g-force. Then, when the engines finally shut down completely and we're either at rest or traveling at a fixed constant speed, that g-force goes away and we're in 0g. And guess what? The book and movie are pretty accurate to this too. The movie doesn't touch on the fact that the ship is accelerating so hard that Grace is experiencing more gravity on the Hail Mary than he would on Earth, but it does accurately show that when the ship is accelerating, he experiences gravity, and that when he's at rest or moving at a constant speed, he's in zero gravity. In the book, he finds out that he's in space because he drops something, notices that it falls too fast, goes, "No, that can't be right," then does a bunch of maths to find out that everything on the ship is experiencing 1.5 g, and from that information, he'd have to be in a constantly accelerating spaceship. It's all pretty accurate. However, unfortunately, it is in the constant acceleration flight plan that we find the seeds of the biggest error in the book and movie, but we'll put a pin in that. In the meantime, let's think about how long it will take to get to Tau Ceti if we use this constant acceleration. Unfortunately, because the velocity is constantly changing, it's not as easy as just grabbing our speed and distance and going from there. However, once the mathematics dust settles, we find that it's a little over 13 years to Tau Ceti. Wait, hang on. In the movie, the computer says that the flight plan will only take 4 years. Is that a mistake? No. Someone watching from Earth will think that it took the Hail Mary 13 years to get there, but Grace genuinely only experiences 4 years.
That's relativity, folks.
At the beginning of the 20th century, Einstein changed the field of physics forever with his theories of relativity. The two central ideas were this: the speed of light is constant, and nothing can go faster than light. Not ever. The ultimate result of this insight is that if the speed of light is constant no matter whether you're moving or at rest, something else must be going on. The solution? time behaves differently at different velocities. The faster you go, the slower time moves. This way, light is always moving at the speed of light no matter if you're looking at it from the point of view of the person in motion or someone watching from the sidelines. This is the idea that has been named time dilation, and it is real. According to general relativity, this time dilation should also apply to gravitational fields. If you're in a strong gravitational field, time will move slower than for someone outside of it. This is real enough that satellites in orbit of Earth have to have their clocks calibrated for the difference between the speed of time on Earth and the speed of time in orbit. That difference is minuscule fractions of a millisecond, but for a computer it does make all the difference. The point is, time dilation is real. And the thing is, it does affect you and me when we drive to work or even get up and walk. But the velocities that we move at when doing these things is so much smaller than the speed of light that any time dilation we experience is mathematically irrelevant. It is only when we get up to significant fractions of the speed of light that it becomes a noticeable phenomenon, and the factor by which time is dilated is found through the Lorentz factor. This might look like an ugly equation, but I actually find it really elegant. Okay, but can we pretty please go at the speed of light and see what happens?
No, you can't. Don't even try.
Through the Lorentz equation, we find that the Lorentz factor of an object moving at the speed of light gives us a divide by zero error. The fun implication of this is that time dilation for anything moving at the speed of light is infinite, and that as far as photons are concerned, the particles that make up light, any travel they undergo is instantaneous. As I said, I find it an elegant equation. Unfortunately, this equation assumes a constant velocity, and the Hail Mary is doing the constant acceleration flight path where the velocity is constantly changing. Fortunately, people cleverer than I am have come up with equations that can work out the time difference. They look like this. To be specific, these are the equations we use, which find the travel times for the first half of the flight. To find the total travel times, you just have to multiply these numbers by 2. I hate trigonometry, so I used an online calculator that employs these equations, and hey, look at that! 13 years to Tau Ceti from Earth's point of view, and a little under 4 from Grace's point of view. The book and the movie are right about that too. Perfect! Incidentally, this is also why Strat is so much older than Grace at the end of the film. She's lived something like 26 years in the time that Grace has lived about 8, thanks to traveling at relativistic speeds. So we're in a pretty good spot. We know how the astrophage work. We know the flight plan involves constant acceleration, and by extension the amount of acceleration we're using. We know the time it'll take to get there, both from our point of view and Grace's. The only thing we're missing is how much fuel it's going to take to get there. Hey, there's an equation for that too! Let's say you want to know how much fuel it's going to take to get somewhere. Under ideal conditions, you only need a few things. You'll need the mass of the spacecraft itself, which is known as the dry mass. You'll need to know how fast the fuel you're using is going to be shooting out the back of your craft. You're going to need to know the delta V, or in other words, the total change in velocity the spacecraft is going to experience. Put it all together, and you get this formula, which tells you the wet mass of the spacecraft, that is, the dry mass plus the mass of all the fuel you will need. If you want to find the ratio of fuel to dry mass instead, you can just rearrange the equation to look like this. This equation will tell you how many kilograms of fuel we will need for every 1 kilogram of spaceship. With everything we've learned from this video, we should be able to put this together without too much pain. We know that the fuel leaving the ship is straight up light, so it will leave the ship at the speed of light. We know that the ship will experience an acceleration equal to 1.5 g for about 4 years. Be careful, we want to use the Hail Mary's time point of view here, not Earth's. So with these numbers, we can find the total change in speed it will experience on that trip, or our delta V. We plug all of this in and find that for every kilogram of spaceship we have, we will need 415 kilos of fuel. It says somewhere in the book that the Hail Mary weighs 100,000 kilos. So all in all, we will need 41,500,000 kilos of astrophage to make it to Tau Ceti. Hang on. That can't be right. Do you know what this means? The numbers are wrong. The numbers are wrong. In both the book and the film, Eva Strat tells Ryland Grace that to get to Tau Ceti, they need 2 million kilos of astrophage, not 40 million. In the book especially, this amount of astrophage is a headache for them because they have to figure out where to find the energy on Earth to breed and enrich that much astrophage. They straight up destroy the entire Sahara by covering it in solar panels to be able to generate enough energy to breed 2 million kilos of astrophage. This amount of astrophage is a hassle to make, so much so that the Tau Ceti mission has to be a one-way trip. They just do not have the time or energy to make enough astrophage for the return journey. But according to the maths, 2 million is nowhere near enough to get to Tau Ceti.
No, it's bad. Grace Rocky dead. All Rocky plural. All Earth die. We die. We die.
So, what went wrong here? Is Andy Weir just making up numbers? Well, no, he's got all the right equations, he's just applied them the wrong way. See, the equations I showed you for the time it takes to get to Tau Ceti are the ones that we use. These equations account for the first half of the trip where we're constantly accelerating in the direction of Tau Ceti for 2 years. Now, for the time calculations, you can just multiply the results by 2 to get the full travel time with no hassle. And for the first half of the trip, if we run the numbers, we do get a ratio of 20 kilos of fuel for every kilo of spaceship. In other words, 2 million kilos of astrophage. But Weir's missed a step. He's got the fuel for the first half of the trip, but forgotten to do the maths for the fuel for the entire trip. Okay, so no problem. We've got the fuel for the first half of the trip, so we can just multiply the number we found here by 2 like we did the travel half times and get the final required amount of fuel. That means we only need 4 million kilos of astrophage, right? Well, no. The problem here is that the faster an object with mass goes, the more energy you need to apply acceleration to it. This applies to acceleration in any direction, so it doesn't just mean you need more energy to speed something up, you need that insane amount of energy to slow it down as well. So if you want to slow down and enter orbit of Tau Ceti, the required fuel of the trip isn't double the amount of fuel needed to speed it up, it's the square of that figure. It's not 20 kilos of fuel per kilo of spaceship, it's 400, so 40 million kilos of astrophage total. By the way, this is part of why it's impossible to get anything with mass up to the speed of light. As you approach the speed of light, the energy required to accelerate the object shoots up to infinity. Basically, you need an infinite amount of energy to accelerate anything with mass to the speed of light. Now, does this mean that Earth is doomed? I mean, they were already panicking about trying to make 2 million kilos of astrophage. There's just no way on Earth they're making 40 million, right? Is Earth just dead in this scenario? Well, no. There is hope yet. See, I'm not the first one to pick up on this mistake by far. Apparently, someone braver than I am not only noticed the mistake, but emailed Weir to say, hey bestie, we think your numbers are wrong. And he got a response. As it turns out, Weir had intentionally calculated the fuel for only the first half of the trip initially, but then forgotten to square that number to find the total travel requirement. So he was very aware he'd made an error in his work, but he had a patch for it. Don't accelerate for the entire trip. Okay, so don't hit me, this gets a bit mathematically involved. But it's worth it, I promise. So in Weir's proposed fix, we start the trip off accelerating at 1.5 g as before. But after we've traveled about 1 light year, we shut off the engines. Thanks to Newton's first law, the Hail Mary would continue at the speed it had gotten to before we turned the engines off, and coast towards Tau Ceti at near the speed of light. Then, when the ship gets about a light year away from Tau Ceti, we do the slowdown burn to bring the Hail Mary to a comfortable orbit around the star. Okay, so how long will this take us to get to Tau Ceti, and how much fuel do we need? For the speeding up and slowing down parts of the mission, we can apply the constant acceleration equations from earlier, but just for a much shorter distance. As a reminder, these equations look like this. So I went to the online calculator and ran the figures, and find that from Earth's point of view, the total acceleration time, both speed up and slowdown, is 3 years. From the Hail Mary's point of view, it's only accelerating for 2.05 years. So let's do what we did earlier and grab the rocket equation. Speed of fuel, still speed of light. Delta V, now the acceleration figure, still 1.5 g, multiplied by 2.05 years. And we get a figure of 24 kilos for every kilo of spaceship. So all said and done, 2.4 million kilos of astrophage. Much better than 41 million. So the $1 million question is, how long does this trip take us? As we found earlier, the speed up and slow down time added together takes 3 years from Earth's point of view and 2 from the Hail Marys. We can also find from this online calculator that this acceleration gives us a peak velocity of 92% the speed of light. So when the engines turn off after the speed up burn, this is the speed the Hail Mary will be going until we start the slowdown burn. 92% the speed of light. The speed up distance is a light year, and the slow down distance is also a light year. Subtract those from the distance from Earth to Tau Ceti, a reminder 11.9 light years, and we arrive at 9.9 light years of coasting distance. Finding the time this portion of the trip takes from Earth's point of view, it's simple enough. 9.9 light years divided by 92% the speed of light gives us 10.76 years. And to find the time from the point of view from the Hail Mary, we can use the Lorentz factor that I pulled up earlier. At 92% the speed of light, we get a Lorentz factor of 2.55, which means that the Hail Mary will only experience 4.22 years of coast time. So, if we add all of the numbers we've found so far together, we can find that if we only accelerate in the first and last light years of travel, the trip will cost us 2.4 million kilos of astrophage and take 13.8 years from Earth's point of view and 6.3 years from the Hail Mary's point of view. Now, while we're closer to our fuel budget of 2 million kilos from the book, we have traded some things off. For one, the trip takes longer. More time for people to die on Earth, more time for things to go wrong on board the Hail Mary. The crew of the Hail Mary spend the trip in induced comas in the book and movie, so 2 extra years in a coma could do untold damage to them. As it was, Grace's crew members didn't survive the flight. Furthermore, not accelerating the whole way means that the crew will now spend 4 years of their 6-year flight in zero gravity, which poses all new challenges to keeping them alive. We've made the fuel budget easier, but we've made the mission a hell of a lot more dangerous. But the thing is, this mission was always dangerous, bordering on insane. To call shooting astronauts at a star 12 light years away in the hopes that they might be able to send data back about how to save Earth a long shot is like saying the Titanic hit an ice cube. But when the fate of the planet hangs in the balance, you have to try. If I'm being honest with you, I nearly didn't make this video. I mean, who wants to listen to me yap about physics for half an hour? I certainly don't. The only reason this video exists is because I found the fuel mass error at 4 in the morning by accident, and whipped myself into a sleep-deprived delirium trying to work out if I was the one making a mistake or if Weir was. By the time I had found the solutions to the problem, it was 8 AM, I had work in 2 hours, and I knew then that this video had to exist, if only to justify the entirely self-inflicted sleep deprivation. This way, I could pass it off as research and not being insane. Never say I don't do anything for you guys. But oddly enough, this has been fun. I mean, there's still all the chance that this is incoherent babbling, but it's given me the opportunity to engage with a story I really love in a completely new way. Yes, I grew closer to the film about the friendship between a man and a rock by crunching some numbers. No, we're not going to talk about it. Some of my friends think there's a series in this idea. You know, the physics of popular science fiction movies. Could be fun.
What think, Earth?
In the meantime, I hope this helped illuminate the physics ideas behind this movie that I dearly love. If you enjoyed it, like, subscribe, ring that little bell, and have a good day.